Alright, in this video I'm going to be showing you how to do the variation of parameters method in differential equations. So let's just jump right into this problem. So we have y double prime plus y equals secant x. So the first thing we're going to do is look at this as a homogeneous differential equation. So you have y double prime plus y equals 0. So that way we could find the y sub c of the final solution, because you know that the final solution is equal to y, and then we have the particular solution plus the yc component. So first we're going to start with the yc component and do that by setting it equal to 0, treating it as a homogeneous differential equation. So once we do that, and then we write the auxiliary equation, so you get m squared plus 1 equals 0. And when you solve for m, you get m is equal to plus or minus I. And therefore, the solution would then look like, so you have e a to the x times sine bx plus e a to the x times cosine b of x. And so the b is 1 and a is 0. And once you plug that in, you would get sine of x plus cosine x. And obviously you have the c1 right here and then the c2 right here. So anyways, that means now that I have the yc component, I could use that to find the yp, the particular solution. So right now we know that yc is equal to c1 sine of x plus c2 cosine of x. Now from this, we could just, we need these two functions. So we have f1 being equal to sine of x, and then we have f2 being equal to cosine of x. Now we could go ahead and compute the Wronskian. So the Wronskian would then be, so we have sine of x, and then the derivative of that would be cosine of x. And then we have cosine of x, and then negative sine of x. So then once you cross multiply, you should get negative sine squared of x plus cosine squared of x. And then that would just be, this is an identity, that would be equal to 1. So that means your Wronskian is equal to negative 1. And let me just clear up some space. So after computing the Wronskian, the cross product, we get the Wronskian equal to negative 1. So now we have to compute a second Wronskian. I'm going to call it Wronskian sub 1. And then that would be, okay, so we're going to put a 0 right here, and then the function, which is this, secant x. And then here we have f2, and then on the bottom, the derivative of f2. So f2 is cosine of x, and then we have negative sine x. Okay, and then once you compute the cross product, you get 0. So it'll be 0 minus cosine of x times secant x. Well, if you simplify the secant x to 1 over cosine x, then you just get negative 1. So y sub 1 is equal to negative 1. So now that we got that, I'm going to clear up some space. Okay. And then, so we have y, or you know, let me just write this. Let me put this in a box. And then we have y sub 1 being equal to negative 1. And now we have to do one more Wronskian, and I'm going to show you where this is going. So the second Wronskian is equal to, okay, so we're going to have f1 right here, and then the derivative of f1, which is cosine of x. And then here we're going to have a 0 and then f. And this f would be the secant x, just like before. So that's secant x. And then once you do this cross product, you should get, let's see, that's sine of x times secant x, and then plus 0, minus 0. So sine of x times secant x, so once you multiply these two, that would be sine of x times 1 over cosine of x, which simplifies to tangent x. So that is tangent of x. And that would be your y sub 2. Okay, I'm going to go ahead and clear the space. Okay, so y sub 2 equals, we said tangent of x, tangent x. Okay, now that we got these information, so the particular solution, what we're looking for, yp, has a template of this. It's v1 f1 plus v2 f2. So what v1 is equal to the integral of y sub 1, w sub Wronskian 1, and then over the Wronskian. And v2 would be equal to Wronskian sub 2 over the Wronskian. And if you just plug this in, we get the integral Wronskian sub 1, that's negative 1. Oh no. So yeah, that's negative 1 over negative 1, which is 1 times dx. That means v1 is equal to x. And then if we plug this in, we get tangent of x over negative 1. So that's just a negative outside of the integral. So the integral of negative tangent, well, in the first place, the integral of tangent x is equal to ln secant x. We have a negative right here, so that'll be negative ln secant x. And from another identity, this simplifies to positive ln of cosine x. Or you can just keep it this way, either or. Either or works. So, okay, so that's our v2, this is our v2, this is our v1. Therefore, the particular solution right here, this one, oops, come on. All right, so, whatever. So yp is equal to v1, which is x, times f1, which is sine of x, plus v2, which we said is ln cosine of x, or negative ln secant x, same thing. Okay, like that. And then times f2, which is cosine of x. All right, so that's the particular solution. And finally, the entire solution, as we said, is equal to y sub p plus y sub c. And that right here is our y sub c. So we just combine everything together into one entire general solution. So that would be x sine of x plus ln cosecant x times cosecant x. Okay, that's the y sub p part, plus c1 times sine of x plus c2 times the cosine of x. And that entirely would be your general solution. And that's it.